Okay, welcome back to C467 Geotechnical Engineering Design 1. This lecture, we will talk about the deep foundations. There's two parts of deep foundations. First, we talk about the axial capacity, and the next lecture, we'll talk about the displacements, which is like the settlements you anticipate when you design for deep foundations. Kind of like systematic with our shallow foundations. First, we talk about the bearing capacity, and then we talk about the settlement. Same here, but now we go into the deep foundations. And for this particular lecture, the learning objectives are: first, we will learn how to find the nominal axial downward or upward load capacity for different piles and different shafts. So when we say piles, you imagine those would be metal piles, steel piles, and when we talk about geo shaft, that will be those P-board concrete piles. And also we will learn about how to interpret static load tests data. We will also talk about the pile group effects. So by the end of this lecture, you will understand, at least have an idea how to design for a group of piles, not just a single pile. And the reference for this lecture, you go back to your textbook, chapter 14 to 16. So first, before I go into talk about the deep foundations, let's talk about like what are the difference between deep foundations and shallow foundations. Theoretically, you can design for shallow foundations to however large you want, which means like you don't need to theoretically you don't need to worry about deep foundations if your shallow foundations can be however large it can be. For example, if you have a warehouse that you design for with a really high loading from the structure, you could design foundations that shallow foundations that is super large, however large you want to goes into. In that case, this foundations means to be able to carry the loading, but it may not be cost effective or even be feasible, right? Because you may not be able to excavate that amount of soil, or maybe at some point you just like the material pull in for your concrete foundations or your mat foundations, the rebar that you need to put on, it will be way too expensive than the structure itself. So the alternative for that is you design your structure to support by deep foundations, which means you're passing the loading to the bedrock level, or like the another like soil formulation or soils like formulations that have a much higher soil strength. So this could be the bedrock or other like a stronger material. So the loading here now is kind of like a pass by the soft material that you may have. That like if you need to do shallow foundations, you need to have a super large mat foundations. Now you pass all the loading to the bedrock. So the rule of thumb, is how to make the cut off, like how to call which ones should be used. There's some rule of thumb criteria. So shallow versus like a deep foundations. The major cause again is about the cost. So when to upon that doing a deep foundations will give you like a better economic factors, or you'll be cheaper than like you're doing a shallow ground foundations. You can imagine if you have a typical like small project like kind of like a warehouse or like residential house or couple story buildings, a a shallow foundation is the way to go, because the loading is not that high that you need to build a real large mat foundations to support all the loadings. But if you have like some really like a large structure like a high-rise building, or like even like some offshore dual platform that you have receives a lot of like a loading that you expect, then deep foundations is the way to go, because you need to bypass the loading. It's so high that you need to give it to the bedrock, such that like you can sustain the structural loading. So some general rule of thumb is if you end up like the area of your foundations is greater than like 1/4 of the building footprint, and you may be the way to go to the deep foundations. Or like for the case that like you have very soft soils in the upper portions of the soil stratum. So if you have soft soils in upper layers, then you may want to do a design for like a deep foundations, because the soils that your mat foundation is founding on is so weak that it cannot sustain much loading. So maybe you become more instead of like do all excavations, get rid of the soils, and then backfill with good materials. You may be cheaper. Just do a deep foundation, bypass it. Or like for the case that you have very large uplift pressure. So we don't have much chance to talk about uplift scenario, but for the advanced graduate course, which will be offered next semester, CE 567, which is in the graduate level, and I think like the prerequisite is just like a this course. So as a undergrad here, you can take a graduate level course with special approval. If you're interested, like talk to me. I'll talk to the department chair. We can grant you the pass that take a 5,000 level course and use this to substitute your 4,000 level cost. So if you're interested in further learning about this geotech design, I highly recommend to consider that next semester. Take the geotechnical engineering design number 2, CE 567. So if you're interested, like talk to me. The other factor it could be is maybe you have a very large lateral loading. It could be something like from the wind loading or earthquake loading, that like if you are lateral kind of like a loading to your structure. For example, you have wind loading or earthquake loading that like you're adding on a structure. Sometimes the deep foundation is a better way to go. And other scenario maybe is when you have your structure is the design criteria, it must like penetrate through some water depth, certain depth of water. So at offshore environments, this would be ideal, right? For example, like this is the seabed, and like this is the water. So this is the water, and you have a dual platform here that you want to like oil platform pumping that you need to build. So the only choice you have is you have a deep foundations. Go to the sea. This is the seabed walk or the seabed. That like so you can pump out the oil from this platform. So in that case, like there's very fascinating civil engineering project building a platform offshore. So in that case, you may want to do the foundations too. So the list here is kind of like for you to factors to consider. Okay, so in the design of deep foundations, in piles, either driven piles or geoshelf, there's two major mechanisms that we need to pay attention to when we consider the capacity of the deep foundations. So the two mechanism is the first one is the toe bearing capacity, and the second one is the side frictions. So it tells you how the deep foundations work in terms of where the the resistance or the the loading capacity come from for the given piles. So for the first, we will talk about the toe bearing. So this is the two mechanisms that we need to understand. So first, let's talk about the toe bearing. So on the picture on the left here, describe the toe bearing in the deep foundations and compare with the shallow foundations. So on this bread footing here, or this like a kind of like a mat foundations, this is what we understand. This is what we have learned in lecture 3, right? So when we talk about those shallow foundations, you have the loading given from the structure, passes to the footing and then to the soils, and here at the base of the foundations, you get the pretty much the bearing, which is the loading divided by the area. So this is our shallow foundations, and for our deep foundations, the geometry is just quite different. You can tell you make up two parts. So this, we have the same amount of loading applied on the foundations. There's two sources of support. So the first support to resist the loading, first is the toe bearing here. The second is the side frictions. We'll talk about side friction more. But first, this is the toe bearing that we have. And the toe here is the toe. So this one is the toe bearings, and this resistance here that you have, this toe bearing, you can think of it similar to the bearing capacity we learned in shallow foundations. And this is like the bearing pressure in shallow foundations. So F and D's foundations. So some terminology at the tip of the piles we call it toe, and at the opposite sides when the part that connect to your structure or connect to to columns or above ground, the other end we call here is the head. So each deep foundation piles, we have the head and also we have the toe. And the shallow foundations, right? We also we calculate the weight of the foundations. So the same thing here for deep foundations. As part of the analysis, we will also need to consider the weight of the foundations. So WF. So WF here is the same thing, right? It is the weight of the foundations, weight of the piles. And some simple calculations for us to find the toe bearing. So first, we will calculate the gross toe bearing. So the gross toe bearing is equals to loading at the head. You got like the loading got like a transfer and so forth and so on, and you will becomes the resistance, the toe bearing at the bottom, So the gross toe bearing at the bottom will be equals to P sub T divided by the area at the toe. We will talk about in the later slides to talk about how to calculate the area of the toe. It's a little bit tricky. And so again, the area of A sub T is the pile toe contact area with the soil. So this area is important, the way that like calculate it, because it's affect your. So if we subtract this with the weight of the foundations, kind of like because the weight of the foundations, the directions is opposite to the resistant force of the toe bearing. So the polarity of the two is opposite to each other. So if you also consider the weight of the foundations, the toe bearing that you calculate over there, we call it let toe bearing. So that's what we learned for the first mechanisms, the toe bearing. The calculations is straightforward. But like finding the loading at the toe could be a little bit tricky. We talk about how to do that, and also we need to be very careful on how much of area you consider. We talk about this in later slides too. But the first mechanisms, that's how we get the toe bearing capacity. The second mechanism is the side frictions, because when you drive the piles into the ground, and the difference between the major difference between a deep foundation and a shallow foundation is that since it go deep, so the contact area at the side of the of your piles is significant. So the side area is, this is a long pile, right? Versus you just have a little bit of like a contact at the side in the shallow foundations. Because of that, so you have a lot of contact area, and no matter clay, you have the cohesiveness. Sand, you have the granular frictions. Those no matter what type of soils, it will contribute some resistance, and it can be significant that it helps a lot in our design. So the second mechanisms is also very important that we need to account for, and thus we'll be coupling with the directions of the loading. When you have downward loadings, where the compressions type of loading, which in the mold case, so because most of the loading are static, that low, then we will have upward. Sorry, you have upward frictions to counter your downward loading. And on the other end, when you have upward loadings, then your frictions will go downward. And there will be a case that you have a moment adding on your piles, but the moment part will be we won't have time, or this will be too complicated for this class. So the moment of the piles, we talk more in the graduate level foundation design class. But for the frictions, we do need to be aware of the directions of the loading. Is that compressions or tensions on the piles? So most cases, we have compressions, but in some cases, if you have a wind loading, adding on your offshore platforms, then your piles, you kind of experience kind of a cyclic loading, because if you have for example, you have a dual platform offshore, so this is the water, and this is the dual platform, and this is the seabed, and you have the foundations. The deep foundations go into the seabed, and when you have a wind loading adding on, so this piles you have a moment, and also you have back and forth kind of like a wave loading, sea wave loading, or wind loading adding on your structure. Then like your piles will kind of like experience like upward and downward loading. So in that case, you need to design for both scenario. And for side frictions, the design will be the side frictions to calculate that will be equals to the side force divided by the area at the side being contact. So this is P sub S is the side force, and A sub S is the side contact area. So if you have a rectangular piles, a dual draft, or like a circular steel piles, then that's the way that you calculate your side based on your geometry. And this F here is the side frictions. But very, very important, there's a concept you need to accept that this is not like a static frictions. This are dynamic frictions, because when you drive the piles, you mobilize the soil around it. So this is a mobilized side frictions. We'll talk about this. This is displacement dependence. So when you think about soil behavior, again, you need to think about a stress strain curve. So does the interactions, the structural soil structural interactions between the piles and the soils. The performance, the strength or the capacity that you gained from the soil strength, it just depends on the displacements, how much soil you have mobilized. So this is the mobilized side frictions. And for the case that we have a downward load, so this is the downward loading. The nominal force from the frictions will be equals to, because since this is going down, and the one that resisting is also come from the capacity, the bearing loading at the toe. So this will be equals to the bearing capacity at the load times the area at the toe. So A sub T is the pipe toe contact area, and then plus the summations of frictions times the area. So this is the side frictions, this is the side area. We have a summations here is because this is a very likely you have a long piles, and the piles will go through different soil stratum. So each soil stratums, you may have a sand layers on top of a clay layers on top of a silt layer, and at different soil layers, different soils will give you different side frictions. In the later part of this lecture, we'll talk about how to characterize the side frictions based on the soil strength. So the frictions that you gain is kind of like a soil strength dependence, and with that, you will have different layers of side frictions, and to calculate the total capacity of the piles from the side, then you add up all the layers. So that is the downward loading. And when we do the upward loading, what being different now is you need to encounter the force that being opposed to the loading on the top. So the loading for the upward loading will be equals to the weight of the foundations, because now your loading is pointing up, but your weight is kind of pointing down, and this will be equals to plus the summations of side fictions again times the area. So pretty much this is we need to consider the effect of the variety, the loading directions. And again, like the downward loading, we take care of the weight already, because like this Q sub n is the ledge toe bearings. So whenever you have a pine over there, which means like you have already been correct for the weight of the piles. So again, like we will this kind of like give us a overall picture, and then we will get into more details on how to calculate the toe bearings, because you need to care about the area at the toe again, and on the side frictions we talk about how to characterize those frictions, which is very important, as you can see here, how this frictions relate to the soil properties. That's what we will focus on next, and such that you can get the nominal loading that you can get from the side of the pile. Okay, so mobilizations of soil resistance. So when we were talking about the side frictions in the previous slide, we bring up this important concept in geotechnical engineering. This go back to the soil behavior. When you learn your soil mechanicals, CE366, or when you go to the lab, right? You have done the unconfined compression test or the direct shear test. You get a stress strain curve of the soil. So when we want to fully understand how the soil behave, the stress strain curve is a good demo. So this could be displacements, which if you normalize the displacements by the specimen height, you get the axial strength, or like the shear strength for the direct shear. So also the loading, right? If you have the loading divided by the specimen area, you get the stress. So this is the stress strain curve. Or if we go back to the raw data that we measure, it will load displacements curve. We get a curve, right? When we load on this our soil specimens, we did not get a single number. If we get a single number, if you test our soil samples, again, this is the stress strain curve again. If we test on our soil samples, we got like a single number, kind of like a straight line, horizontal straight line. In that case, you can only use one number to represent the soil strength. This is what you get. It's always true, no matter how the displacements change. But in fact, no. In soil behavior, it is a stress strain response, which means not until a certain displacements here, you are fully mobilizing the soil strength. So that's what the mobilizations means. Mobilizations of soil strength or mobilizations of soil resistance, because before certain displacements, you are not getting the full capacity of the soil strength. So that's why soil or geotechnical engineering is much complicated, behavior-wise, than some other material like concrete or steel. Those can be more straightforward because you can use perfectly elastic or perfectly plastic model to describe the stress strain models. But for soil, it's highly non-linear plastic material. So that's what makes geotech fun. Anyways, when we think about this, the toe bearing and the side frictions, it kind of like a stress strain curve, because the principle are the same. You are loading on the soil. The observations that you have, you will be kind of like the stress strain response you have in the lab that you have measured, right? For unconfined compression tests or the direct shear test back to CE368 Geotech Lab costs. So a typical response is you need to account for the soil strengths that you get is a displacement dependence. So if you do a more complex modeling out of the scope of this class, like some finite element programs, or some more advanced like 2D or 3D modelings. You will input the stress strain response of the solid elements in the software. But in more like analytical approach, like you use like a single formula to calculate the overall resistance of soils. Like what we'll be doing next, we realize like we account on some type of like factors, either factor of safety or like some correction factors, alpha method or the beta method we talk about later. Those could be a factors of 0.4, 0.5. Part of those factors, you penalizing your soil strength is because you need to consider the mobilizations, like an issue here. That the fact that soil is a strength dependence response parameters, and also like for more advanced analytical models. They may have another factors or parameters for you to input to represent the displacements. So when you drive a piles, so this is the ground. So when you drive a piles into the ground, the soil will settle with the piles, because pretty much you're pounding the soils. You're mobilizing the soil, so put it this way, especially at the toe. So you're causing the settlement or the mobilizations, or this is the toe, and also you're mobilizing. Actually, there's some down drag right there. So I'm talking about downward loading. Upward, there will be the other way, around for the side frictions. But let's assume. We only have downward loading here. Actually, at the side, the soils is also settling, because you have kind of like a force right there. So you are having like a small amount of settlements right there at the side, right at the side of your pile. So right here you have all the settlements, and those settlements will represent being part of the mobilizations of the side frictions. So this is just like kind of like a concept, and like number wise, or analytically how we handle this. We will talk more. We'll come back to this when we get to some like approach to characterize or to quantify the side frictions of the toe bearing. Another important factors that contributes to the toe bearing is the contact area, and actually it's not just the toe bearing, but it's also the side frictions. So so when we calculate those like loading or the loading capacity for both the toe bearing and side frictions, the contact area is also the key. So again, we have two types of areas. So we have the A sub T, which is the toe bearing. So we have the A sub T, which is the toe bearing area. And also we have the A sub S, which is the side frictions contact area. So those are the two areas we need to pay attention to. So for so at least for the toe area, when you have co-section piles, so for examples, so if we have a co-section piles, we can consider the full area. So what does it mean by co-section piles? Like imagine you have a concrete drill shaft. So the cross sections area, the whole thing is like a solid. Or very rare that you have or maybe timber piles. So in geotech or like in offshore environments, we use a lot of timber piles because timber it has better water resistance than other material of like concrete or steel. And if you're lucky enough, like you can recover some like recycled like poles, power poles, or like the old days the light poles, like make up with timbers. Those could be very economic, like a material for your project. So when you have a solid like a coast area, then like you have a coast piles. So you will consider the full area for the tow. But many cases like for steel piles especially, you have open sections pile, which is the case that like you will have a hollow like the geometry. So now the question is, when you have a hollow piles, should you just consider the metal part, the steel part, or like what about the open area, the hollow part? Should we consider that to be our contact area here? So for the tow bearing, actually, like you can consider the open areas too, because what happens is those open-ended like steel piles, when you drive the piles into the ground, you kind of like will create a soil plug, and the soil plug here you may have a chance to give you a full contact area. And this is important because the toe bearing, the toe bearing, the contact area is the key on like giving the bearing capacity. If the fact that is just giving you like a full contact, and you are not accounting for it, end up you will be over designing. You will waste a lot of money on like for the project. And so some rule of thumb is like the saw plug. When can we consider like take advantage of like the saw the saw is being plugged or not? It actually depends on how far the piles have difference. So we can consider that's like a saw plug. Rule of thumb is when the depth, when you drive into the soils that far enough, so the depth divided by the diameters of the or the single dimensions of the piles. Usually this is the diameters, so this is the depth and this is the diameters. If the ratio is about 10 to 20 for clay, then yes, you can consider like there's a saw plug. And for a sand, you need like a little bit more distance. So if the ratio is about 25 to 35 for sand, then yes, then you can consider that's a saw plug, and then you can consider like you have the full area that you can take advantage of. And for this is for the toe bearing. So this part is for the toe bearing. And for the side frictions, the similar thing. Now if you have H piles, this is the H piles. If it's fully plugged, this is how the soils and the piles like work together. As different piles, or like you maybe just like over half plug. So that also depends on how far the piles have difference, and and different like design standard may give you different criteria. So you need to pay attention to that. If you're doing according to what type of design criteria, you better go back to the the design manual. And also the salt plug is nice at the bearing, toe bearing, but the side frictions you need to be careful, because the side frictions, it could be like if you're fully plugged, then now you only have this much of contact area. So if you're fully plugged at the side frictions, you only have like the kind of like the outside, right? Pretty much you only have this part of like a contact area. But if you are at side frictions, that that is just like for partially plug or like a not plug scenario, then you may have a little bit more like a side contact area. So those are the different design scenario you also need to think of for like the area, and it highly depends on what you try to design for, or like should you consider what kind of scenario. So you need to be very careful when you do your deep foundation design. And many times, like you better reference to design standard, or like any like a reference you can find, or some case is like highly depends on like how deep you go. Is that go to a depth that like great enough that you feel comfortable your deep foundations is fully plugged, so you know that you will consider the total area at the bearing, and also just the outside area, not counting any like inner area for the side frictions. Okay, next, let's look at some design method, or like overall design approach before we get into the details on the geotech design of deep foundations. First, the approach that we talk about is the allowable stress design method. So what we call is the ASD method. So this method is very like a traditional geotech focus, which like your allowable capacity. So this is kind of like piece of A is the allowable loading capacity. So this is the allowable. So the P used to stand for the loading, so you would expect the units is like a pounds or kilonewtons. So this is the allowable loading capacity, and this is equals to the nominal loading. So P sub n divided by the factor of safety. So the factor of safety is, whenever you see a factor of safety, it means that is a deterministic type of approach, which is the old school geotech method. So this is kind of like for downward like compressions loading, and be aware that like for upward loading, for tension design for piles, you will have come up with different like loading capacity. But what being different is now you have a new upward loading, nominal loading capacity, and then you may have a high effective safety. So the table down there, give you a sense on how the downward loading and upward loading in terms of the factor of safety made difference. So this table here summarize like some recommended values for the factor of safety based on the pile. So again, like there's different type of deep foundations, either like different piles or like a P-drill shaft or concrete pile. So the driving piles likely is could be like a metal, like steel piles. But like you can be like a concrete piles being different too, but more likely concrete can be like a P board, and then like casting concrete, and that is the drill shaft type of piles. So here this table is for steel piles. So you, once you change the piles, like the next table, the next slide actually is nothing like difference, but like you have another set of factor of safety that is for the drilled shaft. So this is design factor of safety for the drilled shaft. Anyways, so those are the factor of safety, and again, like highly depends on whether you are doing compressions or tensions. Those value can change, and again, the piece of n are the nominal. So those are the nominal. The N stand for the nominal allowable loading capacity. Nominal loading capacity. That's the piece of N, and it can be either tensions, or which means like a upward loading, or like a compression loading, downward loading. So the key now, the geotech part is how to come up with this piece of N. How to come up with this like a nominal loading capacity. That will be the geotech design that will be focused on this lecture. And the big picture of like coming from this value, you have a two approach. You can either like determine from field tests, or we will do a bearing capacity analysis. So those bearing capacity analysis will be similar to what we are doing for the shallow ground foundation design, right? The soil strength, and you have the Kawasaki factor n sub c, something like that, and then like based on different like geometry and soil type, then you come up with the bearing capacity for the shallow ground foundations. So we'll go into details to talk about each of them, how to come up with a piece of N of the field test, and also using some like bearing capacity analysis. This is like kind of like expensive, but this is the field test can always give you a set more accurate results, because it's just site specific, and you can modify your field test to mimic or to become like exactly what you want to do for your project. So but this is not cheap at all. But bearing capacity analysis, what you need is soil parameters. So kind of like back to lecture number 2. You do all those CPT, SPT, those good stuff, and then like or like if you have some historical boring log data, or like you understand you are on a very limited budget, but you just based on geology, and then get some very quick very rough soil properties or soil strength parameter estimations, then like you can give you something to start, which is the bearing capacity analysis. And we talk about how to do that too. So this what we want to do next. For the rest of the lecture, where we talk more about the field test and also the bearing capacity analysis. So again, like this AST method is straightforward. You will come up for your design, which is like this piece of a allowable loading capacity. You imagine like this will be highly integrate with the structural engineers, because the structural engineers will either hire the geotech or the geotech structure work together as a subcontractors for the pipe. And what we geotech get paying for is this to come up with the allowable loading capacity, such that we can pass this to the structure, or the structure will consult with us, work with us, and then to find out how to increase this number to meet the structural design. So this is the allowable loading capacity, and as you can see, it highly depends on the two factors. So you need to understand where does the factor of safety come from, and what kind of uncertainties you have, and also you need to understand how to come up with the nominal loading capacity. And you have two ways, either field test or bearing capacity analysis. And the factor of safety, again, if you can see on this table, if you have a little bit more cohesive soils, or actually as you can see on this table, if you have a static loading test, so this is kind of like the field test. So those are the field tests. So if you're given the field test data, then your factor of safety can be lower. So in that case, which means you are more certain. But the wave equations analysis and the pile driving formulas, those are done while the contractor driving the piles. So it's not like a specific test to try to fail the soils or fail the piles to get the true capacity of the piles. So those are those factors of safety means you're not paying extra money to do a dedicated test, and so that's why the factor of safety is a bit higher. Similar thing here, this is for the drill shaft. If you do have static loading tests, then you realize your factor of safety actually is lower. And for other soil conditions, if you have very erratic soil behavior or soil conditions without a static loading test, then your factor of safety is very high because you want to compensate the uncertainty. So as a geotech, the design, many of it, when you get out of school and then work for a couple of years, you realize this is like a business. It's we love the engineering part, but essential in this geotechnical engineering consulting business, there's always a business component that you need to understand, and you need to know how this business work, and how the monies work, and how the site investigations and also the engineering concepts all come together. And you need to make recommendations to the clients, or make choice as a project engineers, which way, which investigation program or the whole design process, the whole package. As you can see here, should you convince your clients to spend the money upfront to do the field tests, to do the static tests? It may cost you extra 20K at the beginning. But you realize, if you have done the static test, the static field test, and then end up you can use you have reliable data, and then you can have a lower factor of safety for design. End up overall maybe you will save you end up saving a lot of money in the design part, because if you are not certain about the strength of the soils, or the strength or the nominal capacity of your pile, or the allowable capacity of your piles, of your deep foundations, then end up this uncertainty will cost you maybe a lot more money than you spend the time and also the budget upfront to do the static tests. So what is the cutoff point, and when should do what, that's highly depends on your project. So that's the fun part of geotechnical engineering. So those pretty much is the is for the ASD design method. So again, like the key concept of the ASD method is you highly rely on the factor of safety. So the factor of safety is capturing an uncertainty, and of course, like you also need to understand where this nominal loading capacity come from. We talk about more next within like 2 slides. We start talk about a field test. So aside from the ASD allowable stress design method, there's also called our RFD method, the load and resistance factor design. So this design philosophy or this design approach is more like a structural sound, more like structural base. So instead of one factor of safety, they try to break down into different factors. So again, like kind of like the nominal. The allowable loading factors now is a factor that nominal capacity will be equals to 2 factors. So you will use this positive structural design. So this come together more like just like the allowable loading capacity will be equals to different factors. So first we have the tip resistance factors. So this is the tip, the toe bearing part, and then plus the side frictions part. So the factor of safety approach, the AST approach, pretty much you combine this two with one's factor of safety. But here you break it down into 2 parts. You have the correction factors for the toe bearing and also the correction factors for the side frictions. Such that you come up with this allowable loading capacity, and this is for the downward loading. So for the compressions type of loading. Likewise, you have the tensions or the upward loading. So this is the upward nominal allowable capacity. Then you need to worry about the weight, right? So this is the weight of the drill shaft and the weight of the unit weight of the materials, and then time the weight, and then plus. So this is kind of like the correction factors, and then time the weight, and then again the side frictions, correction factors. So this is the upward. And this table here gives you an idea what kind of like resistance factors they recommend for different scenario. And this is for different piles. So this table is for piles. And the reference for this table is from AASHTO. So kind of like the transportations, like a design manual. So because like transportations, they need to build a lot of like embankment for the highway, and oftentimes they need to use deep foundations. So they do have the guidelines, the references on how those to be built. But anyways, those are different piles recommended values for the resistance factors. And also that's like other like design scenario using the RFD when we talk about all this like alpha, beta, gamma method more when we use the more like so those belongs to the method that we talk about using the bearing capacity analysis. So this is more for you have a field test. And now this is more like you have the bearing capacity analysis. So this is from static analysis. So that's why you see those like analysis. You don't have a field test, site specific data. So you have a high uncertainty. So to like correct from the uncertainty that you have, or the account for the uncertainty that you have. So you have a factors that's kind of low compared with like where you have specific site-specific experimental data, field test data. Then you have factors kind of much higher. So with that, like then with a higher factors, and you can see that like you will have a higher nominal, a higher allowable capacity for a structural design from the foundations. Okay, static load tests. So this slide explains how the field tests is being conducted. We talk about this. This being important, and also this being expensive, and also being like a very important part for the design for deep foundations, because it can provide site-specific data. So the whole idea is pretty much like for a project, for example, a high-rise building. There will be maybe like a 50 piles to support one structure. Then like think of like those piles, you may have a lot of group piles like come together. Then end up you have 10 groups of piles that each group have 5 H piles going down into the San Pedro formations at the downtown Los Angeles. So since you have like enough amount of piles need to be installed, so you better do it correctly, and you have the budget to spend on like doing one static load test, which means like think about it, it's pretty much just like felling. The whole idea is like driving a wheel piles at the same site until it fell. So since you need to build that many piles, and you have a large budget to work on, so it's ideal that you go out there before installing any piles. You do a few static load tests with one test pile. Sometimes we call it to be the pilot piles, or pilot like a pile driving. We do before even like design for the deep foundations. So well, that's pretty neat like to do that. I still remember when I was field engineers of my first year of my career. So as a geotech entry-level engineers, I got sent to the sites a lot. There's a lot of different like field assignments. Many of them are sample collecting or field observations, getting those SPT, CPT, observing those like field tests, and collect some soil samples at certain depth. But I guarantee you, like the most exciting thing to see in the field, as for the geotechnical field engineers, especially at entry level, is to seeing those static load tests, pile driving tests. And if you work at the large office, for example, the AECOM office at downtown Los Angeles, you may have 5, 6, 7, or even like like a 10, 20s, like a few engineers right there. This is the most wanted jobs at the entry level, because indeed, like it's fascinating. The complex of the instrumentations, and also you got to see how the piles are being measured, and also loading the piles to the point of failure, which is quite fascinating for engineers to see. But anyway, so this picture here shows you the setup for the static load test. So this piles here is the test pile, and in order like to test on this piles, we need to have the load frame. So this is the whole setup is kind of like the loading frame, and the whole thing will be powered by a hydraulic jack. So you'll be like the setup here, the trailer behind the whole setup is kind of like a hydraulic pump behind it. So you could provide the power to the jack, which allows you to provide the power to load on the piles, the test pile, until you fail. So either you can do a compressions or do a tensions loading. Depends on your design and depends on the site conditions and what you want to look at. So and then you will have a load cell. So this is kind of like a load cell connected to the piles. So in the real picture, zooming in the real picture, this is the load cell. So the load cell will pick up the loading that the piles experience. So the resistance provided by the piles until to the point of failure, and we want to record the stress strain relationships, just like your unconfined compression test. Remember in the lab, you measure both the loading and also you measure the displacements, such that you can get the stress strain curve for the response of the soil. Here is a little bit more complicated. You got the load displacement response of the piles and soils interactions. So when you lower the piles, it's not just the piles, because you also mobilize the soil around it, both at the toe and also at the side frictions. We talked about the mobilizations a couple of slides before. So that what exactly you will be measuring, because you take some displacements for the soil fully engaged with the piles, both at the side frictions and also at the toe. So we need to measure the displacements, and those like LVDTs. So those are kind of like a more advanced dial gauge of measurements. In the old days, the field engineers will measure it manually, reading the dial gauge, just like what you have done in the soil lab for a consolidation test. You can remember the machine deflections exercise we do together in the lab. Reading the dial gauge. So that will be the old school, and or we can install those sensors. So both the load cells, this case, or nowadays, both the load cell and the displacement reading by the LVDT. So LVDT stands for the linear variable differentials transducer. So which is set up to pick up the displacements. So now, you got those engineering units, both displacements and low in voltage, and then you can convert that with calibration factors to go back to the engine units. So you get the pounds and also centimeters readings. So you get the interactions between the piles and the soil, and also you realize that those displacements is installed on some reference beams, because when the whole thing in actions, the pile is moving, and you need to have the zero reference points to know the displacements. So those the reference beams is kind of like being stable in the ground. So so they will be anchoring far enough from the loading pile, so make sure the beam is not moving, but the pile is moving. So the relevant difference in terms of locations is the displacements that you want to measure, such that give you the response of the piles when you're mobilizing the soil. So this is the picture here, of the overall setup in the field. I hope some of you will work at a geotech engineer at some point in your career, and then you'll be sending to the field, and then you can observe those pile testing, static load tests on piles. If it comes up I know within the area, within the regions, there's projects they're doing the pile static load. If you're lucky enough it happens. It's kind of rare, but if it happens, maybe not this semester, maybe a few after the pandemic situations. I mean, if I can, maybe I'll organize some field trip for the students to go on site to see this. So this is kind of one of the very cool thing that I think is a very good field experience that everyone can learn. But anyway, so that's the overall setup, and the final products for the static load test are those curve. So those like a pi response curve. So that's why we are measuring the applied load versus the settlements. So the load, we pick up from the load cell, and the settlements is pick up from those early DTs. And the shape of the curve depends on the soil type. And if we have some soft soil, so some soft clay to medium clay, we will expect like the response of the curve as something look like this A curve over there. But if we have some very stiff clay or like a sand soil, we will expect a stiffer response, which is like the curve of B here. So this curve will be the field data that we generate like from this field test will be very useful. Remember what we're trying to achieve, right? We talk about all this is try to find out the nominal loading capacity. So the curve that we generate from the field test, and also we mentioned like this can be obtained from the field test. So the field test that like we look at, the data we look at will give us the piece of N. So the next slide we'll talk about it. Okay, so we talked about the field method, how to come up with the static load test curve, which is something like that, like right. So from the field we do our test results, then we get like a response curve for driving the test pile. So now the question is like from this test pile results, how do we find out the single number for the nominal loading capacity for us to calculate the allowable load capacity for design. So from a curve, how to come up with a single number. So that's what we try to do. And the Davidson method, which will guide you through how to come up with a point from a curve. Again, the whole concept is the response for the power and soil. It takes mobilizations. It takes settlements to fully mobilize the soil. So that's why you got a curve, how the loading respond are related to functions of the settlements, the displacements. And out of this curve, which points do you use? If you pick the early on one, then you have such a small load that you are way underestimating the capacity of the piles. And if you take later on, then you have a very large loading capacity that you are maybe overestimating. So this Davidson's method will provide a reasonable estimate to pick somewhere the piles has been fully mobilized, but not yet being too optimistic. So realize this Davidson method is kind of like rule of thumb for you to get started. And if your design have if in the future your structure, your project, your design have very different design criteria, you need to be very careful. Okay, if you have you work on for example, you work on super soft soil, then the soils will be easily being mobilized. Then that the Davidson approach is kind of getting somewhere mid-range. So this is the Davidson method. Realize you try to pick a point kind of in the middle. So if you know ahead that your design will be everything is kind of like a displacement related. You know that like you're kind of like expecting large displacements, then you may want to use the values that represent that. Versus you have a very small strain or small displacement pile behavior, then you may want to use a smaller displacement. So highly, this Davidson method, is nice as an approach to guide you how to pick a number, but you need to understand this. You're engineers, so you will make the call in the future. And again, like as geotech, we get paid well, and we get paid well. It's not just like following the cookbook. At the beginning of a career, like you try to learn, like you try to fit in, try to find your lead, you try to find your expertise. That's fine. Take a time to understand how things work. But at some point of a career, you need to be good at something, and people will look up to you if you work your way become an expert, in certain area. So which means you can make the call, what kind of like a design number should what kind of design scenario we should focus on based on your project's criteria, and also maybe the soil response. In many cases, the two come together for the project. But anyways, here we try to introduce you the Davidson method, how to pick up the one single number for used to design for as the nominal loading capacity. So now we have a curve. So the Davidson method is like the very first step is to perform the field test. So after you perform the field test, then you get the curve. So this is the first step. Is establish the load test results to to plot up with the pile loading with the displacement, which is the settlements. And the next step is establish the y-intercept. So this is the second step. So this will be this is purely empirical. So the Davidson method is purely empirical. Again, the purpose is they try to pick somewhere at the midpoint and have some guidelines for you to do that. So such that you can use one point for analytical analysis. So this y-intercept, if you use the SI unit, it will be 4 millimeters plus B is the foundation diameters divided by 120. If it's just like a British unit, that would be like a 0.15 inch plus like a B over 120 again. So you get the y-intercept. That is the second point. And the third point is the point, and then you try to establish a slope. So this is the getting this slope or calculating this slope here is your third step. And this slope is equals to the foundation depth, so how deep the foundations go to, divided by the area, cross sections area of the piles or the drill shaft, and then times the modulus of elasticity. And realize for different piles, for steel, will be straightforward. You will be like a constant material properties. But if this is concrete, you need to use have the F sub C. But in many cases, you may have a drill shaft, and for drill shaft, that is concrete with a steel reinforcements. I hope you have take your concrete design class at 4000 level, so we learn about all this good thing. So you have steel reinforcement plus the concrete. So those are the drill shaft. So when you calculate the modulus for the composite of steel and concrete, you need some you need a formula. We talk about that. So the F sub C again is the compressive strength at 20x day. So for your material class, you should heavily cover that. So this is the Davidson method again, which first you have your pile test, static load test, and then second step, establish the y-intercept by this simple calculations, and then extend this line with a slope with right there d over a times e, and then like you know the point, the slope, and whenever intercept, that will be your ultimate capacity. So you can use that for design. So this is the piece of n. In the other way is like this point here will be equals to the point times the slope, so you will get back this point. So this is the piece of n too that you can use for your ASD method, the allowable stress designed method. So this is the Davidson method, which is quite handy, and that's maybe something like you will work on as an entry level engineers. When the pile driving data come to your desk, then your task maybe will come up with the ultimate or the nominal loading capacity for foundation design. So that's why when we try to do this, there's two approach. For field tests, you pay the money upfront, you get very reliable test results that measure both toe bearing and also side frictions of your piles at the same times. And next, later on this lecture, we will move on to the bearing capacity analysis. We realize that we need to isolate the two mechanisms and calculate each of them at a time. Okay, next, I want to discuss another type of field testing. So this may be a little bit advanced, but I want to introduce in our business, like how fancy the instrumentations for deep foundations can be. This may be a little bit rare because using strain gauges, which we'll talk about here, can be very expensive. Because at the end of the day, those sensors they use, first of all, they are more accurate and more expensive, and also some of the sensor that will go with the foundations could be just one-time use. Anyways, so the whole idea here is we understand. Actually, we keep on emphasize on this is the behavior of geoshaft or piles, deep foundations, is highly displacement related. Which means, again, the concept is you need to mobilize the soil both at the toe and also at the side, such that the response of the interactions for both structure and soil, which means the piles and the soils, they can go together. And it highly depends on the mobilized displacements. And in order to capture the displacements, the best way to do it is using the strain gauge to measure the deformations. And you don't want to just measure at one locations. Remember the pile driving test, you have the RDTs installed at the head, which is above ground, right? And pretty much you're just measuring the settlements from the top at one locations. But the strain gauges can be fancy. You can install at multiple locations throughout the piles. So for examples here, you have this piles, and you're proposing to install strain gauges at 5 different locations. So you have either like a strain gauge of the low cell at the top most of the piles near the ground surface, or somewhere at the toe of the piles. And here's a picture showing you the instrumentations. So you have the latest strain gauge there. Hope you can see it. And what being difficult is not just the sensor, but all the wiring that you need to come with it, all the sensing cables. You need to go all the way from the top where you you have the data logging systems and go all the way deep to the ground. And usually you do it for deep foundations. I mean, it's like really deep foundations that are supporting very important structure, like some high-rise buildings that have more than 100 levels, or like something very important, like the drill platform offshore, the oil productions that relies on firm foundations that at the middle of nowhere at the sea. So those are extremely important structure, expensive structure, with going very deep into the ground. And the challenge is not just placing the sensor in the ground, but like having all the cables reaching deep down, going through all the adverse environments, like corrosive soils, or maybe all the salt water, and your cables need to induce all the travel and all the installations, and also sometimes people look at long-term performance. Maybe you want the sensor and back in the ground for a long period of time, a couple of decades. And also very important, the longer you go, if you understand electrical engineering, the longer you go, the more noise that you will receive from the from the data logger, and then you need to process the data. So all of them is like an art, and this very like good engineering work is rare, for using strain gauge for a typical project. But I do want you to see like it works, and it works well. And it could be a possibility that in the future you come across multi-million type of or even billion type of budget projects that you will work on some of those instrumentations. I think it will be fascinating. Anyways, also you can see like the sensor they use and all the cable you use. Very likely those are just for one time locations measurements, or like one project measurements, and no way you can recover the sensor and then you for the next project. Pretty much you embed those sensors in the ground, and then you go with the piles at the locations. Sometimes you want to log the data for a long period of time, especially if you your project is hooked up with a university like us to get funding doing research. Want to know about the long-term performance of piles, or very special soils, or very special design that worth do the research on. Very likely it could be a master or PhD thesis or projects you guys maybe in the future working on. Anyways, those are the strain gauge setup that I want you to at least to be aware. And all those are the again the instrumentations using strain gauge. Okay, next, let's talk about the bearing capacity analysis based on soil properties. So we finished talk about all the field tests. They are nice, and but you need to also have, as engineers, you also need to have understanding that those field tests is very expensive. Oftentimes, for based on the budget, you may not have the luxury to perform like in situ field tests. And same thing apply for your semester project. So your semester project is you obtain your soil properties through site investigations, either CPT or SPT, and from them, you can generate the soil profiles, and then the strength parameters. And also soil classifications, all the good things we have learned through our in geotechnical engineering, and then from those characterizations, then we can do bearing capacity analysis, and that's will be what the rest of this lecture about, how to come out the nominal loading capacity for your piles. either driven piles or drill shaft based on soil properties and analytical methods. So before we start talk about that, we need to understand some procedure. There's some construction. There's some kind of like a flow chart for us to go through before we come up with what kind of equations we're going to use and what kind of design method we should follow. It highly depends on, first thing is the construction method. So we could have for construction method, we could have piles, like the driven piles, like the steel piles. We have and other on canvas. I put on other YouTube resources for you to look at how the construction method, from shroud foundations, mat foundations, and also for dip foundations. There's two main kinds. First, there could be like the driven piles, or next you could have the drilled shaft. So those make up the construction method. So these two are the same categories. The first thing we need to look at is what type of construction method we have. So it could be like the piles, or it could be the drill shaft. So drill shaft. So for the piles, likely this is steel, and for the drill shaft, likely could be a concrete pile with steel reinforcements. And for the for the different piles, it could also be like a timber piles. So it's more like the mechanism on how the constructions take place. So the different piles are the one that you don't alert the ground. You directly like punch in the piles, so you drive the piles to the ground. But the drill shaft is you will have a pie knot holes first. So you will do the drillings, and then you have the pie knot holes, and then you will put in your reinforcements, and then you will have the put in the concrete. So this YouTube videos, this clip over here give you a very good idea on how the drill shaft being installed. So first you have the pilot hold to remove the soils. So the drilling can do that. And then you go to the depth that you want. So pretty much the bottommost a layer is good materials that you want the toe bearing to add on. And then you put in the reinforcement, the steel reinforcements, and then you will have the concrete to pull in, and end up very likely the foundations is supported with a column. So the loading directly go underneath to the pass through the foundations to the good bearing material. So that is the drill shaft. So first thing we care about, very important, is the construction method. Next, we need to work on is the loading mechanism. And we have, as we talk about this at the beginning of the lecture, for each dip foundations, no matter the driven piles or the drill shaft, there's two loading mechanisms. First is the toe, the second is the side frictions. So same thing here. Same as the drill shaft. So this is the the loading mechanism that you need to think of. And for each type of construction method, it owns like a loading mechanism. And third is like our analytical analysis will be based on the soil type. So each of that has the sand and clay. Sand or clay. And it belongs to each loading mechanisms. So which means like, at the end of the day, you will have 8 different types of analytical approach based on all the scenario here. So when you think of like which equations you should use, or like how the foundations will behave, or like how the numbers work out, you need to think of what kind of construction method, loading mechanisms, and what soil types we add. So at the end of the day, you have all this like a flow chart you need to think of. This is the soil type. Well, anyways, and the soil type also dictate what the drinking conditions, especially when we deal with the side frictions. So for sand, because like the pore water will drain out quickly, so this can be done with effective. So this can be done with like an effective stress analysis. You can do the effective approach versus the clay. You will need to work on the total stress approach. So same as the side frictions that we work on. So sand again is like we oftentimes use the effective stress approach, and the effective stress, and for the clay we use the total stress, because again like during the construction time, either when you're like driving the piles or pre-pour the piles, like during that period of time, whether you have enough drinkage time for the water to excess pore pressure to be dissipated. So that's make the difference. Should we using effective stress or total stress analysis? And we will come back to the details for each of the scenario. But the effective stress analysis, we used to use the alpha method. So we will talk about what is alpha method later. And for the clay method, we have the like effective stress sand, we have the beta method, and for clay, we have the alpha method. So we will come back to talk about what is those. So this is kind of like the big picture on how to deal with the bearing capacity analysis based on soil properties. Again, like with the absent, if there's no field tests, like what we talk about, the static load tests or the strain gauge installations, because oftentimes those are very expensive instrumentations, or you don't have the informations, or like the field tests need to be done before the constructions. Anything you want to go back to analyze the bearing capacity for the piles again, you need to use those analytical approach. If you have some studies you want to study like on existing structure, or like you have a tunnel that you're going to go through some existing structure in the Los Angeles downtown area, there's no way that you can do a field test anymore, because the structure is there. You cannot like remove the structure and then perform a field test. So your options there will be just doing those bearing capacity analysis, and which equations or which like approach you should like use. First, you need to think of what type of construction method is it, And then like think about the for the construction method, you need to consider both the toe and side frictions, and like which equations for each of these categories here depends on the soil types. So first, let's look at our first scenario where we have piles. So we have piles here, pile, and then we look at the toe bearing capacity. So what we are working on is, again, if I may, go back to this flow chart. We are looking at the piles, and we are looking at the toe, and then we look at the clay. So and then we look at the sand. So for this slide, we start with the driving piles. We looking at the toe, and then we start with the clay. And the nominal bearing capacity. So this Q sub n here is the toe bearing capacity for clay under effective stress, and is equals to N sub C times SU. So SU is the undrained shear strength of soil. So you can estimate this either from lab testing or like the field testing, like the SPT or CPT analysis that you have go through. And the concept, you realize that this is very similar to the shower ground, the shower foundation design. Our bearing capacity is equal to one of those like a Tersaki factors times the undrained shear strength of soil. Now we are only dealing with clay, and this N sub C, one of the Tersaki factors, is equal to 9. So this is kind of like straightforward for the toe bearing for driven piles for clay materials. So the concept here is similar for the shower ground foundations. When you're loading on the mat foundations, you kind of like create like a the punching shear that like you have a shear failure surface, and same kind of like a same thing of the deep foundations. When you load on it at the toe, the bearing capacity when it beyond the loading is beyond the bearing capacity of the soils, and what happens is you will create kind of like this type of punching or local or punching failures. Okay, so this is the toe bearing capacity for the clay, and this is considered like effective stress conditions. We have a water table there, and again, this is the toe bearing. This happened here. And for the sand, you could be a little bit more complicated. So the toe bearing capacity will be equals to B, which is the diameters of the piles times the unit weight of the soils, and then first like a Tersaki factors N sub I gammas, and then plus the effective stress at the toe, and then this is the N sub Q and other Tersaki factors, just like the bearing capacity from the shower ground foundations. So the B here is the pile diameters, and the gamma pi here is the buoyancy. Is the buoyant. Unit weight, which is equals to the total unit weight minus the unit weight of water, and the effective stress, this terms here is the vertical effective stress at the toe. So you're calculating the effective stress at this point. And the toe bearing capacity also based on two Tosaki bearing capacity factors right over there, n sub gamma star and also n sub q star, and the procedure to calculate those. So according to the Rorschach method, it's the same thing, the similar thing we have learned from the shroud ground foundations. The shroud foundations. So those n sub gamma and n sub q there, those are the Tosaki bearing capacity factors. So there's a couple ways to there's two ways to do it. First, you can calculate the n sub sigma first, and n sub sigma is related to this I sub r, the rigidity index. If after you calculate your rigidity index, that functions of the Poisson ratios and I sub r, then you can find out the n sub sigma, and the n sub sigma it can substitute to these equations. Then we can find out the n sub q pi, and the n sub q pi, if you substitute in these equations, then you can find out the n sub gamma. So n sub gamma and n sub q's are those two bearing capacity factors that you need to find out the toe bearing capacity for the piles, different piles in sand. And or the other way is like you can read off this n sub gamma pi with this design chart. So if the soil friction angles, you calculate I sub r, then you can find out this n sub gamma. And if you know n sub gamma, then you can also find out n sub q pi. So if you want to stay away from this like a lengthy equations, you can use those design chart. But nowadays, with the computation power that we have, those calculations is not too bad. So I hope this start give you feel in the picture what we are doing. So again, the bearing capacity analysis approach highly depends on the construction method, loading mechanisms, and soil type. So we just deal with the driving piles for the toe. So for example, we find out for clay here, the normal capacity will be equals to n sub c times the undrained shear strain of clay. And the sand here, we just deal with the toe bearing capacity for the different piles. So this, the Q sub n will be equals to the B times gamma pi. So this pretty much is like the Rorschach method in shallow ground foundations. But we just look at the toe. There's more to come about the side frictions we talk about later in this lecture. Okay, so here to show you a table recommended by API, the American Petroleum Institute, for some recommendations for the sand piles. So sand is very tricky. You don't want to overestimate the strength of the sand that you have, the toe bearing. So this table here pretty much is based on different soil type of the sand density. It has a cutoff value. So which means whatever you calculate here from this Rorschach bearing capacity equations, it should be cut off by this recommended values. If you have very loose soils, actually API even recommend using CPT based method. This equation doesn't work. And again, those analytical equations is come with a lot of uncertainty. And the worst case scenario is you don't want to have this bearing capacity equations to overestimate what the actual capacity of the piles that you have. So based on different soil, for some like denser soil, so when you get to medium dense sand or sand silt type of soils, you have different like a maximum cap. So if you, for example, if you have a very dense sand soil stratum that the toe bearing of your piles is bearing at, and if you calculate the loading capacity, the toe bearing capacity for your piles at very dense sand is 15,000 kilopascal. So API recommends you that don't use like a 15,000, use 12,000. So those are something that you need to pay attention for when you have different piles and on bearing on sand. So again, if we go back to our big picture, when you're doing your driving piles, so driving piles you're doing on the toe for the sand capacity, but you use this approach. You all use this like Versic type of bearing capacity equations. Be very careful. That's like a maximum cap recommended by API, the American Petroleum, so not API. So American Petroleum Institute. Okay, so let's move on to talk about the side frictions. So we'll start with the different piles again. So the basic principle is think about like you have the foundations, kind of like a board is sliding against the soil, and the soil does have horizontal stress. Remember back in 366, we talked about the basic concept that the ratios between the vertical stress and horizontal stress is with the factors of K0 at rest conditions. And at the beginning of this semester, if you go back to lecture 1, we also discussed like different scenario for the horizontal stress ratios. So again, the K is the lateral earth pressure coefficients, which is equals to the horizontal stress divided by the vertical stress, and it must be in effective stress space. And this K constants is kind of like functions of the displacements, the K0, at rest, active, and also passive conditions. So again, all this we have highlighted at the beginning of the semester. So if we go back to the very first one at the beginning of the semester, right here. So we talk about all this like a horizontal stress, which is the K parameters. Is you have 3 status, either at rest, passive, and active. But it depends on like how much displacements are you into or away from the soils, and also these are functions of the movement. So that is the horizontal stress, and the K is the lateral earth pressure. So if you want more information, so I highly recommend you go back to lecture 1, slide 16, and listen to the lecture again. But anyways, so the concept here is we want to find out the side frictions. So this is the different piles, and we do have a frictions that is under the loading of the horizontal stress from the soil. So we want to find out like this frictions. So this frictions, I get back to physics when we learn about static. The frictional force here now is the effective horizontal stress times the friction coefficients, and the friction coefficients will be the horizontal stress, and this mu, this again, this coefficients of frictions there is tangent phi sub f. So tangent well, again, so this first of all, this is the horizontal stress. So sometimes like some textbook will use like sigma pi x. Oh, this is the horizontal effective stress. And the tangents phi sub f, or the mu right here, it is the coefficients of frictions. So this is the coefficients of frictions between the soil and piles. So this is, again, this is a soil structure interactions, not as simple as just like the behavior of the soils or behavior of the metal or concrete. So you have, it can be very complicated because you have two different materials. They're sliding against each other. So we talk more about how to find this parameters, and again, it's like the phi sub f here. This is the soil piles in interface friction angle. So this what it means, and this simple formula will give you again. So this f sub n here is the nominal. Again, this is what we try to find. Unit side frictions. So this all tie back to this very important parameters, the phi sub f, which is very hard to measure. You may have some very dedicated research lab to able to measure that with some like a pull out box testing. But anyways, you have there's some like recommended values there, which is quite useful. So it depends on what type of like a piles you're working on, different piles you're working on. Concrete, like a steel or timber, and for steel, like if you have different geometry that gives you like different frictions, like a frictional surface, then you expect like the numbers will be different. And this is again the number that the parameters that we need. But like this is the soil part, so this is the soil friction angle. So it gives you as a ratios that normalized by the soil properties. So that's why like able to characterize the soil strength is very important. So this also tie back to lecture 2 when we talk about the site investigations program. But anyways, so this gives you a kind of like a big picture on what about the side frictions for piles. Two key takeaways is, first, it depends on the horizontal stress, and it's tied back to what we learned previously about the lateral earth pressure ratios. And also you need to accept the concept that now this is a soil pile interactions, frictions, not just the frictions of the soils or just the frictions of the piles. Is how the two react with each other. So these phi sub f could be like complicated enough to measure. So there's some other method being available, which called the beta method. So we talk about this beta method. So we touch base on this at the very beginning when we talk about the big picture. So this beta method, again, like, don't lose track on what we're trying to do. So all this like a bearing capacity analysis depends on the construction method, loading mechanisms, and soil type. And we are talking about the side frictions for the different piles. So this is actually this whole thing here. If we reference to the textbook, this is chapter 15 of your Akadoodle textbook, and this is chapter 16. So we start with sand, talk about the side frictions of different piles, and we use the effective stress approach, the beta method. So what is beta method? So what beta method work on is try to simplify the nominal side frictions as a wage as a parameters beta times the vertical stress. So some book will say this is sigma z as the vertical stress. I forget what being used in the textbook, but this means the vertical stress. And different researchers in the past, they come up with different formulations to for the beta. So, for example, the Berlin 1973, they come up with this beta equals to K naught divided by K over K naught. So this is the lateral earth pressure, and K naught is kind of like a soil properties. And then the rest lateral earth coefficients and tangents phi pi and times the ratios again. So this is approach to find out beta, and this is from Berlin. So Berlin is a long time geotech professor at Imperial College in England. So this is 1973. Another like more simplified approach is 0.18 plus 0.65 times the relative density of sand. So this is a little bit much more straightforward. So this got to be in decimal, but not like a percentage. And this is by Bu Shan, 1982. So there gotta be more existing like correlations on this beta method. So when you're practicing, then it'll be your choice which correlations you use. But like each time you use our correlations, you need to understand where it's come from, and you need to make it make sense to you that why this method is valid. I highlight like two popular method there. For us to find the estimated beta. So after we know the beta, then we will times the vertical effective stress. So this is the effective stress analysis. So it's got to be like a sigma pi instead of the total stress. So again, the sigma pi here is the vertical effective stress. And the d sub r here is the relative density of sand, because we're only working on sand here now. And like the bearing capacity, so for sand is always tricky. It's very hard, like soils, to estimate with the use of foundations. So API again, it has recommendations on the cap on what maximum side frictions are being recommended to use. So when you calculate your side frictions, always check with my advice is always ask yourself, does it make sense? Because at the end, the nightmare is overestimate the capacity of the piles, and that would cause failure. And always after you got your answer, or you find the loading capacity both at the toe and also at the side frictions, check the number really quick. Does it make sense to you? And those APIs were a very good reference. And if you find out the answer you got, the numbers you get is way higher than those API recommended values, recommended maximum values, then you need to be very careful. I would not comfortable to use those number, given like all the high uncertainty that like embedded in the analysis, and also maybe on the site explorations like a program, the solve parameters that you get. So those API like menu could be handy. So pretty much this is the beta method. So remember, like a lot of this depends on the loading mechanisms and also the type of the piles. So if we go back to our kind of like the big picture, so what we're doing with now is the clay. Given we're looking at side frictions, and this is a different piles, and this is a total stress approach, and we can use the alpha method to find out the side frictions. So if we go back to here, we talk about the total stress analysis for the alpha method. The side frictions for those different piles is as a functions of these are functions of the undrained shear strength of the clay. So it's not friction angle anymore. For clay is the undrained shear strength, and it is a matter of a factor of alpha. And what we try to calculate again is the nominal side friction capacity. And alpha again is the adhesion factors, and the S of U is the undrained shear strength of soil. So this is undrained parameters which give you the total stress analysis. This is the S sub U. Remember, like back in the 366 and 368, we talk about how to convert the undrained shear strength, and also from the field data back to lecture 2 of this semester, we also talk about how to find the undrained shear strength. And different research in the past give you different kind of like correlations between the alpha that we use to find directly, like related to the side frictions for clay piles, different piles. So there's quite a few different existing methods, and they are more or less is about similar in relating the alpha and the undrained shear strength of soil. And some popular one is like the Tomlinson 1957. It's a classic method. And again, you see API again, the American Petroleum Institute. It also gives you some recommendations. So when you come to the point that you need to do your own design, then you need to pick one that again being reasonable for you. So highly recommend go back to read some of the paper, or I think your textbook may give you some ideas where those correlations come from. But at the end of the day, you need to be consistent using the same approach throughout your pile design. The whole analytical approach highly depends on the construction method and loading mechanisms and the soil type. And we pretty much finished the different piles. So now we move on to the drill shaft, and again the same thing. We need to think about the toe. We need to think about the side frictions and each loading mechanisms. If you have different type of soils, then you will have different formulations or different approach to calculate the axial load capacity. Okay, so for the drill shaft, in fact, this is very challenging to find out those toe bearing and also side frictions. And Let's start with sand. So for the cohesiveness, soils, it's really hard to find out the toe bearing actually. Because like different piles, you're pounding the piles, and you may have a lot of record. But for drill shaft, you need to pre-bore first, and then put in the casing, metal casing, and then put in the concrete. So it's highly like project dependence or site to site dependence, just based on the construction method. And Brown et al. So this Brown is Andrew Brown. He went to grad school with me at Texas. He came up with his PhD study. Pretty much is look at this issue. It's really challenging to try to find the bearing capacity for the drill shaft. So he tried to correlate it with a lot of like historical data. He correlate that with the N60. So you come up with the bearing capacity at the toe is equals to 57.5 times N60. So we talk about N60 back to lecture 2. And he capped it with a cap with 2900 kilopascal. So this is the SI unit. And then like for if this is a British unit, it's 1,260, and you cap it as 60,000 PSF. So this is the English unit. So the N60 is the so what is N60 one more time? So the N60 is the mean SPT corrected values between the toe and a depth of 2 times the width of the foundations below. So that's how they get the N60. And we are talking of the toe bearing here. So what it means is like this is a drill shaft. For example, this is a drill shaft. You know the diameters or the width for the piles, and you try to find the N60. That is like a 2 times the width below the toe of the footings. So this is for the sandy soil, and for clay, so for cohesive soil, the toe bearing will be equals to capacity N sub C times SU. So just like the Tosaki equations. But like now this N sub C, because this is a whole different construction, so you have methods, so you have different N sub C, and it depends on the soil strength. So if we have an N sub C will be equals to 6.5 for the undrained shear strength of soils is less than or equal to 25 kilopascal. This is super soft, then your N sub C is low, and N sub C will equal to 8 for N sub U, like which is equals to 50 at the range of like between 25 and 50. Then N sub C will be equals to 8, and N sub C will be equals to 9, the typical value, if the undrained shear strength of the soils or the clay is greater than 100 kilopascal. And for the like a more shallow, more shorter drill shaft, so if the depth normalized by the width of the deep foundations, the drill shaft is less than 3, and you have soft soils is less than 250 50 kilopascal. Then your Q sub U will be equals to this equations, 2 divided by 3 times 1 plus the depth of the foundations divided by 6 times the width, and N sub C times the enduring shear strength. And N sub C will be equal to 9. And this enduring shear strength will be equals to average. So the S sub U here, S sub U, the enduring shear strength here will be the average enduring the shear strength of soils between the toe and 2 times the width below again. So that is pretty much the toe bearing for drill shaft. Actually, like, you know, for again drill shaft, you bear with much higher uncertainty than like a driving piles when it comes to the toe bearing estimations. So for the side frictions, we'll be using the beta method again. Again, the concept is same thing as the driving piles. We try to find out the frictions. So if this is a downward compressions type of loading, then the frictions will be going up. And with static loading pointing downward. So we want to find out the frictions, and it kind of like depends on the horizontal stress from the ground. And just like similar to the driving piles method, the side frictions capacity will be equals to the beta times the vertical stress. So the beta here also already take care of the horizontal stress components, because again, like, you know, this depends on the horizontal stress, but horizontal stress is kind of like depends on the vertical stress from the ground with the considerations of the K factors, the lateral earth pressure coefficients. Anyways, like we talk about this like a beta in different piles will be equals to the K naught times K over K naught, and then so this is the famous like a Berlin equations, tangents 3 times the interface friction angles between the foundations and the soils, and then normalize that with the friction angle. So you see, like, you know, this kind of smart to use the factors here, because these two cancel out, right? But like the friction angle of soils is something like much easier to characterize than the soil foundations interactions friction angles. Weiss and O'Neill, so this is Texas people again. So Texas, because Weiss is a very famous foundations engineers. He passed away already, but he's a long-time professor at Texas. So Texas has a very good traditions on the foundations design research. So O'Neill, 1988, he come up with alternative for finding those beta method for drill shaft. So beta method will be equals to 1.5 minus 2.471 times the square root of the depth, and this is the SI unit equations, and for British units it is 0.135. So this is the English unit. And beta is capped between 25 and 1.2. So those are the beta values. And Z here is the depth from the ground surface. So this is for the sand. Oops. So this is for the sand material. And for gravels, you can look at this reference. So for gravel, so all this so this width method is for sand. For the gravel, again from Texas, there's a Roland method. So Roland's at all 2005. You can refer to page 586 of the textbook. A similar approach to the sand method, and I don't want to repeat it over here. But like I just want to give you an idea as how to find out the side frictions for drill shaft for cohesionous like a soil. And for clay soils, we use the alpha method. But like, you know, this graph here obviously is very different than the one that for different piles, the same concept, but like different data set. So you have different like results. So again, this is from Texas, from Weiss, the same group of people, Weiss, O'Neill, and Brown. And you could see like how the alpha values depends on the soil strength. And the side frictions will be equals to alpha times S sub U. And you put, you know, the way it works is you have a bunch of like measure data from the field, and then like they try to do a curve feeding, and then they will come up with this design chart. So if you know your unjust shear strength, then you can do your calculations to read the chart, or like some formula they provide, then you can find out the alpha values. And there's also another method called the Coué and Jackson 1989 method. So they like use other group of data. So those are people from Cornell, the East Coast. They come up with the alpha method is with these equations. So PA is the 1 atmospheric pressure, which is equals to 2116 PSF, and then divided by the soil strength, and they cap this as 1. So if you plot this the equations, because alpha is the y-axis and SU is on the x-axis, you will get similar, maybe slightly different curve on the chart. So different like those are the two very popular design method to be used for practice.